From this point on, I'm going to use a virtual board, guys. Let's see if it is going good or not. If it is good, I will continue this way. Okay, so let's say, so after we have learned the direction of current and induced current and induced electric field. Extremely sorry, sir, I don't know why I'm fumbling. So the next section is EMF due to rotation of coil. Okay, now you have to derive an expression. We have to do some of the problems, right? So EMF due to rotation of coil, this is something which you have seen in your daily life. Actually, at least you know a little bit theory of it, right? That is the generator, right? Generator is based on this theorem or this theory only. So before the or here I will deal with even AC, that is generation of alternating current. So actually this topic is something which has to be carried forward to your next chapter, AC, right? So this chapter comes off, or the AC chapter just comes after this electromagnetic induction chapter. So listen to this topic properly, guys. Okay, so we are going to have or consider two magnets. Say this is north pole and this is your south pole, and you are considering a coil. This is something you have seen? Yes, right. Now say this coil is rotating, guys, with an angular speed of omega, right? Not a new thing, right? Let's see, we are going to draw it in an elaborate way because some of the angles have to be marked. So now I'm going to draw just the magnetic field lines, guys. So I hope you understand which pole is north and this pole is south. Yes. Now I'm having a coil like this, right? Now this is a way in how it is just facing such a way that this coil is not cutting the magnetic field lines, right? Very easy to understand. So I can say the flux cutting or flux is zero. Yes, because now it is arranged in such a way that no field lines is passing through this plane or through this coil, right? Now similarly, if this is the magnetic field lines, right, and I am having a coil in such a way that it is arranged in this way, now the plane is in such a way that it is obstructing the field lines. That means now phi is not equal to 0, right? This much should be understood, guys, right? Now suppose I have to understand, or I have to draw area vector also. So let's draw the coil in a larger way. This is my coil, right? And say this is the magnetic field lines, right? Now how will be the area vector be? It should be in this direction, right? Hope you understood. Perpendicularly drawn from the face of the coil, sorry, right? Now what is the angle this area vector is making with respect to magnetic field? I can just draw a dotted line like this. This is also the direction of magnetic field, right? So this angle, right, this angle, let's say, is theta, right? So this is your magnetic field B, and theta is the angle between B and A, right? Clear? So now in this aspect there is flux lines which is cut by this coil, right? So what is the flux present? Flux linked to the coil is actually what? B into A, right? And there is a cos theta. Before that I have to introduce a term also. Suppose this is a case of one coil. Suppose there are more than one coil, say two coils. So that means I have to introduce the flux there itself, right? Or that much flux has to be linked here. So that's why I'm going to write phi is equal to, in this case, NBA, whereas N is the number of coils. Here there is only one coil, well and good. Clear? Now it is B dot A. That means there is a term pending, that is cos theta, where theta is the angle between B and A. Right? Clear? Now this theta, it changes, right? This is actually in place of which you have learned in rotational dynamics in your +1 chapter 11th class. Rotation means this theta is actually angular displacement, right? So when this coil is rotating in omega velocity, that means this area vector also changes, right? Let's see what happens. Suppose this was your coil and this was your area vector, right? Let's say the magnetic field lines was like this. Just take an example, guys. So this was your angle theta, right? Now next, suppose the coil has made just like this. That is, you can see only the side view, right? So this will be the area vector, and again the magnetic field lines is same. So this angle is not theta, it will be theta dash, right? All the time the coil is rotating, the theta changes, right? Or I can say the angular displacement changes. Clear? Right? So let's say this coil is rotating with an angular velocity omega, right? So earlier we have written phi is equal to NBA cos theta. Keep it as it is. Right. Now this omega is the angular velocity of rotation of this coil. Now that means initially it was omega, next second it might be 2 omega, and like that it was increasing. So this is a uniform velocity case. So after t seconds, right, then the displacement theta, you know displacement theta is equal to omega t, right? Just like the previous section, displacement is equal to velocity into time. Here it is angular velocity into time. So this expression you have, can you understand? I can substitute this value here. Yes. So what I am going to write is phi is equal to NBA cos, in place of theta I am going to write omega t, right? Keep it as it is, because we have little bit things to be dealt, right? So what I am going to do, just in the earlier case I told you, this is north pole, this is south pole, you are having a coil like this. That is, the entire coil is facing you. So nothing is cut by this coil, right? So the flux is 0, I told you earlier, right? Now whereas if the same scenario, I'm just changing, the coil is rotated in such a way that I can only see its side profile, and this is your north and south pole, right? And this is your magnetic field lines. So all the lines are cut by it, so maximum flux there is, right? So the maximum flux, it is happening, right? So that means, and the next second, so if it is rotating in this direction, the flux or the coil was rotating in this direction. So initially in this position, then it reached this position, again it reaches the same, right? But in what degree? Initially the angle was 0 degree, say. Next it became, this is 0 degree, okay? Then it became 90 degree, right? Then it became what? 180 degree, right? Then it became again what? It is becoming 270 degree. Then it is coming back to 360 degree. That's how it is completing us in all rotation, guys, right? So listen properly now. So the flux is changing from 0, then it is maximum, then it is 0 again, then it is becoming negative essence. I hope you understood, right? So this way the flux is changing. Negative means initially, suppose this coil in this direction, it has 0 flux, then it arranged in this way, so maximum flux. So once it again flips in this direction, right, it forms in this form, again it comes back to this position itself after 180 degree shift. So initially if it is having flux 5, then 0, then the next will be obviously -5. Direction, not the value, guys. Okay, so whenever there is a change in flux, an EMF is induced, that is minus d phi by dt. Right, so I just wrote earlier this phi is equal to, remember, we written as NBA cos omega t, right? Now we are going to substitute this value here, so it becomes minus d by dt NBA cos omega t, right? Now we have to differentiate this term. How would I differentiate it? I'm writing it again. NBA is a constant term, so I will bring it outside. D by dt of cos omega t. So how would I express it? What is the differentiation of cos A or cos x? D by dx of cos x is what? Minus sin x. Right? Clear? So here, but the problem is along with x there is a constant term, right? So that constant has to come outside. So answer is minus a sin x, right? So here also it will be minus nba, right? Minus omega sin omega t. Right, so bring the omega outside and minus comes off, it becomes plus nba omega sine omega t. Right, you got an expression for induced EMF, guys. This EMF expression is very important. See, as you can say, this EMF E depends upon time, right? As the time changes, EMF also change, right? It is not constant. So in the case of a coil which is rotating, EMF is never constant. It changes with time. This much is clear. I hope you understood this much portion. Right. Now that means, let's move on. When is EMF maximum? So you had an expression EMF is equal to NBA omega, what? You had sine omega t. Right. So if sine omega t's value is equal to 1, so E will be equal to NBA omega. That is the expression for maximum EMF. Let's say that EMF I am going to write it as E0 or E0. This is the maximum EMF that can happen in a coil when it is placed in an external magnetic field and that coil is rotating, right? So if that means the EMF or the magnetic field is not constant, right? It is constantly cut off. So 2 times the value of EMF is becoming 0, right? Why? The sine omega t first term can cause 0. Right, angle can change, then it is becoming maximum value, then it becomes 0 and the next value will be minus 1, like that, right? So when the coil is rotating, a magnetic field is induced now, right? And now not magnetic field, when the coil is rotating, the current is induced, right? So this EMF actual value, right, this much term I have written as E0. So I am going to write for any time t, EMF at that point inside the coil can be written as E0 into sine omega t. Right? So this is actually, you can say that is a wave equation you have learned in your 11th class. It's a sine wave equation, right? So this is the induced EMF equation. Clear? Now suppose what I am going to do is, this coil, we had a coil between 2 magnets, right? This is north, this is south, right? Let's say this coil is connected to an external resistance, say R, right? So the current has been flowing through it, right? This is the magnetic field lines, right? And the current has been flowing. Suppose the coil is rotating in this direction, right? So the coil is causing a current induced in it. So EMF, right, current means I have to find the value which is V by R, right? So E by R. What is E by R? I am writing as E0 sine omega t divided by R. So what is E by R? I will write it as I, current at any time. E0 by R is also expression for current itself. Let's say that is a maximum current. I0 sine omega t. Right, these two expressions, that is the previous one, E is equal to E0 sine omega t and I is equal to I0 sine omega t. These both the expressions are very important for your next chapter, guys. And this is the expression for all the current which you see in your daily life. right? Remember how the current is produced, guys? Your waterfall, from the turbine, from turbine generator, then you get the current, which is AC, alternating current. You just draw the wave. See, let's say this I is equal to I naught sine omega t, right? For sine value, suppose it is 0 degree, that is omega t is 0, so the wave will start from here. When omega t is 90 degree, it will be I naught. So let's say this is I naught value, right? Then 180 degree sine value goes off, it becomes 0, and like that when you continue, you get a sinusoidal wave, and this is your AC wave, right? So I hope you understood. This much portion is very important for your next portion or next chapter, guys. Now we'll do a little bit problems. Okay. Suppose you are having magnetic field like this, that is, they are into, sorry, outwards, let's say outwards, right? And you are having a coil like this, and let's say this is the axis, so that it is rotating in this way, right? Let's say the radius of this coil is R, right? Now, so you are asked what is the EMF induced in this coil, right? If it is rotating at angle of 30 degree in around 0.1 second, right? It is rotating at an angle 30 degree in 0.1 second, right? So please don't, guys, don't use this equation in BA sine omega t. Why? See, guys, this expression which I taught you earlier, right, it is the EMF induced in that coil for a time period, at that time period, or I can say, you remember nth second displacement, just like that this EMF is induced EMF during the tth second, right? Not for t seconds. I hope you understood. So I will explain it again. See, initially, say we draw a sine wave like this, right? Initially there was sine omega t, right? At some time t, if it is 0, right, so it becomes sine 0 entirely, right? So at t is equal to 0, the wave starts from here, right? Now let's say sine, this you have learned in waves, I'm just repeating it. Omega is 2 pi by t, right? So when the time period is half, right, half of the time interval, so I can say this t, in place of small t I'm writing capital T, right? So that means this t cancels out, this 2 cancels out, becomes sine pi, right? So that is at the half time period, again the sine wave will be 0, this one. Remember, I have taught it, guys. Similarly, at sine omega, when it is, let's say, I will take it as t, right, at the time interval t by 4, let's say it is t by 4, right? So the time period is t by 4, and in place of omega I'm writing it as 2 pi by t. So obviously t cancels off, and there will be only sine pi by 2, right? Sine pi by 2 means maximum value, so the value will be here, right? So this and all I have taught, guys. So the expression which you got, that is E is equal to E naught sine omega t, is EMF induced inside that coil at tth second. Clear? So let's move on with the problem. What was the problem? Okay, this was your magnetic field, right? You had a coil, it is rotating with an angular speed of omega, and the radius is r, right? So you are asked what is the induced EMF when it is rotating at 30 degree angle in 0.1 seconds. That is, in 0.1 second it has covered an angle of 30 degree. This much clear. So we have to go back to the basic, right? So I hope you remember what is EMF equation, magnitude only. I'm not dealing with the direction I will cover in the next section itself in the question. Delta phi by delta t, right? This much you know. So what is delta phi by delta? Delta phi is change in flux, right? So final flux minus initial flux divided by the time interval. This is the expression. So let's see what is initial flux, guys. Initial flux means initially it is at rest, right? So the angle it is making with, that is B is making with the area vector, is 0 degree. It is at rest. It has not yet rotated, right? So phi I will be equal to BA cos 0 degree. What is cos 0 degree? It is 1. So I just write it as BA, right? Now what is area of a coil here? It is pi r squared. I hope you know. It's a circle. So let's keep it like this. So phi I initial, I'm going to write it as B pi r squared. Keep it as the first equation, right? Now I'm going for the next one, guys. That is final. Right. Finally, it has reached such a, see, when a coil is rotating, I just told you, right, when the coil is rotating, its area vector also makes the same angle. If the coil is making 30 degree, means the area vector is also making 30 degree with the magnetic field, right? So phi final is BA cos 30 degree. Right. So what is cos 30 degree? You have to know it is BA cos 30 degree is root 3 by 2. Right. Now initially so and here I am going to write for area as pi r squared and there is root 3 by 2. Right. This is the expression for final flux. What was the initial flux, guys? It was B pi r squared. Right. Now what I am going to do, I am going to find what is final minus initial. If it is initial minus final is also okay because I am writing it inside the modulus. So it will be B pi r squared minus B pi r squared root 3 by 2. Right. So it is B pi r squared. I am going to write it as common. Sorry, it is pi here. Right, and bracket it is 1 minus root 3 by 2. Right, so I can write it as, right, if it had been initial minus final also, the expression just the order will be going off, it's okay. So it B pi r squared 2 minus root 3 whole divided by 2. So I can write it as B pi r squared by 2 minus root 3. Right? Yes. So now I'm going to find what is delta phi by delta t. I just found delta phi has how much? We found it as what? B pi r squared by 2 into 2 minus root 3. Right? Divided by how much second it is covering? It is 0.2 seconds. Right, so it will be what, how much you can find? It will be 2 by 10 here, right? So this comes off as oh, it is in 0.1 second. I'm sorry, 0.1 second, and forgot the question was 0.1 second. So it will be 1 by 10 in place of 1.1. You can write as 1 by 10, and the 10 goes up, so it will be 10 by 2 minus root 3 B pi r squared. Right, so what is 10 by 2? It is 5, right? 2 minus root 3 B pi r squared. This is the induced EMF's equation, guys. Right, now in some, if the option is having 5 into root 3 minus 2, then also the answer is correct because you are taking modulus. Right, so that means they have done this initial minus, I wrote initial minus final, no? They actually wrote final minus initial as it is. It's okay. Clear? Right. Now in between, if they are asking what is the induced current, means for if there an external resistance R is connected to this coil, then it will be EMF by resistance. So EMF just found as 5 what p pi r squared root 3 minus 2 whole divided by, we just have to write smaller if the external resistance is smaller. If the value is given, the calculation can be done. Right. Now the last section which can be asked from here is what is the direction, right? Direction of the induced current. Right. The induced current expression you found or a magnitude you found, what is the direction? So again you are going to use or application of Lenz's law. So again I am going to draw this figure, guys. So keep your hand ready. I don't think you have to use Fleming's law. I just want to make you guys understand, that's it. Right. So initially in this phase, all the magnetic field lines is outwards, right? Outwards, that is towards your face. Right. Now once, that means all the fluxes are in maximum condition, all the flux lines are passing through it. Now as the coil rotates in this direction, number of flux lines goes on reducing. Right, that means I can say magnetic field is reducing. Right, now magnetic field is reducing, that's why an induced current is there in this in this coil. Right, when magnetic field increases, flux has decreased, right? Flux has decreased, magnetic field has decreased, d phi by dt is changing, EMF is induced. Right, now as per Lenz's law, what should be the direction of the induced current? Induced current should be in such a way that it opposes the reason. What is the cause here? Reduction in magnetic field. So in order to oppose the reduction in magnetic field, the induced current should reduce a new magnetic field which causes the increase in magnetic field. Right, initially the magnetic field was reducing. Right, the new magnetic field due to the induced current should be in such a way that it has to stop the decrease. Stop the decrease in the sense it has to cause the increase. Increase in the sense, how can it increase? Say, here the magnetic field is outward. Right, so the new magnetic field also should be in outwards. So that out and out adds up. Right, so that means the magnetic field should be outward, means take your hand, right, thumb rule, so that thumb gives the direction of, should be in outward direction, right? So that the rest of your fingers will give you the current direction as like this, that is in anti-clockwise direction. Clear? Right, I hope you understood. By this handwriting might be broad, guys, but when I am writing, I am just reciting also. I don't think you would be feeling that much of problem. Right, so if you didn't understand the video, you guys can take time and you review the sections again and again. Okay, bye. We dealt with Lenz's law. Right, now after Lenz's law we dealt with its direction. Right, now direction, I took a lot of examples. So there is another way of finding direction of induced current, that is Fleming's right hand rule. Right, so this is, I hope you understood why I am using this section for hands, or why I require pen and paper here. So okay, so Fleming's right hand rule says that if you are having your right hand like this, so I hope you understood how to keep your fingers. Right, so keep your fingers in this direction. The thumb gives you the direction of motion, your forefinger gives the direction of magnetic field, and your center finger gives you the current direction. So this is what? Motion, forefinger, magnetic field. This gives you the direction of current. So while you are listening to the video, please write it by yourself. I'm not going to write it here for you. Okay, this much clear? Right, so we'll do some small problems. And I will tell you what is the problem or why we don't go for Fleming's right hand rule. There will be some errors, guys. So this is it. But some of the problems very easy if you have this idea. So this is a coil you are having nearby. Right. Let's say this coil is moving towards the magnetic field. And how is the magnetic field drawn? It is into the field. Right. So take your hand. Thumb gives you the direction of motion. So the coil is moving in this direction. forefinger has to give the direction of magnetic field, so it is into. So keep your finger like this, right? So in which direction, guys? I'm sorry guys if you are not able to see my hand. And which direction your center finger, it is downward. See, field, thumb, your center finger, it is in downward direction. So how should I draw the current direction? Downwards, right? So then complete the circle like this. So in this direction, if you draw the entire view, you will understand it is in which direction the current is flowing. This is I dash, is in what? Anti-clockwise direction. Easy. Right, now same, I am going to take another example. Same field, let's say, and here the coil is moving away. Right, so again keep your hands, again your forefinger downwards, thumb is in this direction, right? Because the motion is in this direction, and which direction the magnetic field lines or your center finger is showing, right? So in this direction, right? Completed. So in which direction the current is flowing? It is in what? Clockwise direction. Okay, so you found the direction of induced current. Now I will tell you what is the problem of it. Say the earlier section I told you the center finger is downwards. I drew this is the section and I drew downwards. Why can't I draw downward here? I can draw, right? So that is a problem in this case. So you are not sure which section I have to draw according to the fingers, right? So it is better if you go by the actual way of using the Lenz's law as a theoretical section itself. But some of the figures, when you're doing the problems, you will understand those type of questions. NEET, etc. This type of questions you can see a lot. So don't go by Lenz's law because it takes time, right? So very few time can be arranged, or within few seconds itself you can solve the direction of current if you understood Fleming's left hand rule. Along with this class video, I will be uploading a lot of numerical questions, guys. So it will be very easy for you to understand. I think in the previous class itself I said. Okay, it's okay. So if you understood this logic, you can solve that uploaded questions again, so that it will be thorough for you.